So today I'm going to talk about a data set that I collected, about 4 years ago, that used EEG to try to get an idea of exactly how cognitive changes in the brain could change following a training session using something that was described, in tongue-in-cheek video game training. So let me give you a little bit of background on me and what I'm excited about. In general, my research looks to understand how the brain can change across a series of different cognitive deficits. I look at populations that go from 4 years old to 80 years old, both healthy and clinical populations, with the idea that if we can understand how cognitive abilities in the brain change over age and change with potential cognitive deficits, we might then be able to better understand how can we leverage the mechanisms of change in the first place to try to improve these functions in any of these populations in the first place. So there's a lot of ways you can enhance the brain, and amongst them were traditional education, very straightforward. Other ways that everybody knows and our grandparents told us is you go outside and get some exercise, eat right, sleep right, stimulate your brain in some way or the other. Things that are more common these days to try to enhance your brain include neurofeedback and neuromodulation. I think we'll be hearing about some of those later. And when I give this talk sometime to college campuses like at Berkeley, and I say, has anybody ever tried pharmaceuticals to improve your brain function? Usually you see hands go up and then they go back down because kids don't want to admit they've actually tried this and it works. In my case, the thing I tried to do a few years ago was to try to improve cognitive enhancement using a derivative of video games. Now when I say this, I don't mean you went to Best Buy and buy Legend of Honor or something like that off the shelf and played that for 20 hours straight. In this case, when I say video games, I'm describing very precise tools that we would use in a laboratory that we have full control over, that on the surface look like a video game, but underneath the hood have a lot of the adaptive elements and technologies in neuroscience that are specifically targeting certain circuits in the brain. So in 2013, this paper came out and it was featured on the cover of Nature, and it got a lot of press because it was relatively sexy for science in that giving older adults a video game and having them play it for a month, their behavior and brain activity looked like a 20-year-old, and that lasted for 6 months. Now the press ran with that and took it in many different directions that was blowing up more than it had to be or what it really told. But the key finding from this was that a carefully designed intervention using these types of technologies in the first place could really be powerful agents for change in the first place. So this is a data set that, with nurses' help, I put forth that people could try to use and understand not only what did we do here, but what can you learn about the neural signatures of change in the brain doing this type of intervention in the first place. So let me walk you through this to give you a sense of what we did and how we got to this point. So the basis of this game is really straightforward. There's two parts to it. One is what we call a perceptual discrimination task. It's really straightforward. Simply on a joystick, they'd push a button on the screen when they saw a green circle and nothing else. Really straightforward, not much to it. The second part of this game was what we call multitasking. Now imagine doing that same exact task while you were controlling what looks like a VW Bug on an old Atari screen on the road. Now this looks very unimpressive, but to a cognitive neuroscientist this is incredible, like me. So in this case, people were doing the same thing with a joystick, keeping the car at the center of the road, pushing a button on it whenever they saw a green circle and ignoring all of the shape color combinations. So this is an example of multitasking, especially when you compare performance on this perceptual discrimination task doing two things at once versus one thing alone. Okay? So in this case, our goal here was to see how well can people learn to resolve this interference of doing two things at once, playing this kind of goofy video game, specifically in older adults. And the way this study worked was we gave these individuals at the time a laptop that had this game loaded onto it. They took it home, and prior to doing any training, they came into our lab for a series of EEG tests and a battery of behavioral cognitive assessments. They had this laptop at home where they played the game an hour a day, 3 times a week for a month, and then they had them all come back into our lab to see exactly what possibly could have changed in the brain following this experience of playing this game. So what we found was that individuals in the older end of the life spectrum, so again you can see on the right side of the screen, you see decades of life, 20 to 30, 40, 50, 60, 70. If you look at this game as an assessment tool, it becomes very clear the population that would benefit the most theoretically from an intervention would be those in their older ages, 60s and 70-year-olds. So that's exactly the population we targeted in this case. So Lower on the y-axis means you have a bigger deficiency in terms of doing two things at once versus one thing alone. And so our older adults in this study, where it says pre-training, started at about a 70% deficit in terms of their ability to do this multitasking. 1 month later, we looked at older adults that did nothing over the course of a month, and you could see they really didn't improve much. We had another group of older adults that took home a version of this game that had no adaptivity and they had no multitasking basis to it. You can see that they got somewhat better, but not statistically significant, actually, more than the no contact control group. And then those older adults that played this game got to a point where they were basically equivalent to a young adult playing it that never trained on it in the first place. Now that's interesting that it shows improvement, the ability to improve in the brain, but it's not that exciting because so what? You got better at what you practice on. That's not that exciting in the first place, but I'll describe that a little more about that in a moment. What was interesting was the plasticity, was that this group that trained for a month, these abilities persisted for 6 months without doing anything in the meanwhile, whereas the other two groups returned to their original baseline state. So this argued that behaviorally something happened in their brain that was pretty interesting, that it would last for 6 months without doing anything in the meanwhile. And the question really here was, well, what is going on? What actually changed? Fortunately, we can look at a couple of other things they did in our laboratory, which was other tasks to find how much of their improvement relate to things outside of what they trained on, something we call transfer. So in this case, this is a really kind of strange paradigm. It's called the delayed recognition working memory game, where people have to remember the first face on the left, a second face pops up, and a third face, the third one on the one on the far right pops up. And the question is, are the first and third faces the same, yes or no? And you have to simply push your button as fast as you can to say, is that the same face I saw previously, while that second face is trying to distract you. Now in the blue bar, our group that did this training actually got better than the other two groups by far, which is interesting because this is a working memory task, which is different than what they train on in the first place. Similarly, there's another task that's called the TOVA. This is a task you typically give to kids that have ADHD to try to see how well they can maintain their attention over a prolonged period of time and how well they can resist impulsivity. And the same kind of effect happened here, where our older adults in this case that did this training showed these positive effects on this task, showing improved sustained abilities in the first place. So that's great. We had these other behavioral measures, but fortunately, and part of the reason I'm here, is we have these EEG measures, specifically that this group did before and after their training. In this case, we looked at one specific signal of interest, something we call midline frontal theta. For those that aren't aware with this, we're looking at the front part of the head in the middle and a specific oscillation in the brain that goes between 4 and 7, 4 and 8 hertz, and seeing how much power there was in this signal in the brain associated with attention. So for a young adult, if you look at their scalp map, you can see it's kind of hot, it kind of surrounded kind of the front middle of their head. And again, this is activity related to the moment an event of interest kind of pops up on the screen. And you can see this amount of activity degrades as you become an older adult, and it's not quite as focal, it's not quite as powerful, and it's indicative of older adults having a more difficult time focusing their attention at an appropriate point. So if I look at the same thing I showed you earlier, the same figure, and now instead of behavior I show neural activity, you can see that in this case our young adults had much more activity than our older adults I showed you previously. At the moment of time, one of those signs popped up on the screen while they were playing this multitasking game. Well, after a month later, our no contact control group didn't really change. Our single task group got a little bit hotter, a little bit more focal, but you can see the pronounced difference in our older adults in terms of their neural activity. Really hot, really focal, right where it's supposed to be, to the point that this signal correlated with their improvement on the game and these transfer tasks I mentioned previously. There's another way you could look at this as something called long-range theta coherence. So this is how in concert are areas of the brain in the front of the brain and posterior part of the brain working at the same time during the same thing. And again, our NeuroRacer trainer, the one in the group on the far left, is the only group that actually showed improvement in this signal of phase locking. So this is, in general, we've basically found that improvements in this training were specifically associated with early sensory processing and engagement in this prefrontal cortex that led to changes in the brain as a whole. And the question I think of interest here, all right, so how do we collect this data in the first place, a little bit more in depth, and what do we do to analyze it? So here is literally a setup, we'll show you a little video of what this looked like. This is a video of the game, and you can see in the corner of the screen these little flashes occurring. every time a sign of interest popped up on the screen, we simply used a photodiode to capture that moment in time, so we had precise time locking on the screen. And this was being recorded directly in our EEG. This is an EEG trace you're seeing right now, and these little event markers popping up on the screen are simply indicating every time a sign popped up on the screen you saw before, we had a tag in the data that said a sign popped up. Now the analysis of this was really straightforward because of the behavior we're trying to measure. We simply were able to lump all trials of all sign types together at all times and then break it down a little bit further. Specifically, we did a little bit of pre-processing with a high-pass filter, ICA to remove blinks, simply chopped up these events of interest into 2,000 millisecond increments with artifact rejecting anything above 100 and minus 100 millivolts. And then we did some spectral processing in this case. Just baseline correct everything and using a Morlet wavelet. All this was done in MATLAB, and then phase coherence again, a Hilbert transform on these segmented data sets with a baseline correction. Now, some of us are more technical with this case, but the beauty of this is I am more than happy to give not only the data set to this, but to actually give the original scripts I ran to run all of these analysis in the first place, so folks could literally use this data set and see how did you get from point A to point B to C, D to Z? Because as I've been told, this data set was not used or selected for analysis, and at the same time it's kind of a shame because this is probably arguably the most famous data set on cognitive training that's ever come about. It's led to so many things changing in this field as a whole, and its altimetric factor in terms of the impact this paper had is almost with the charts, close to 1,400 these days, which is unheard of. And so I think it's really beneficial for folks to utilize this data set and use it to understand how can the brain change, and associated with a set of data that has gotten a lot of notoriety, especially in the space of cognitive therapeutics using video games in the first place. So with that in mind, I just want to thank Adam Ghazali and Pat, a couple of folks that helped me with this. Either funding sources, and if anybody has any questions, per usual, feel free to email me, ask questions, and you can contact me through Neuroscape or my email. Thanks.